screen yet.
Oh, sorry about that. Okay. And you are the co-host now, and yes, it's recording now.
Ah, there you are, Leela. Sorry. We weren't sure because we usually get an email from you and we didn't see one today. So
Yes, sorry about that. Yeah, I forgot to send it.
but see, you have people so well trained, they showed up anyway. So that's a good sign. All right. We're seeing the wrong screen, Jonathan.
Oh, really? I only have one screen.
We're not seeing the presentation mode. We were seeing or maybe you just hadn't started.
Oh yeah, I didn't have it in presentation mode. So just let me see if I share this. Are you seeing the slideshow?
Not yet. We're just seeing your PowerPoint.
All right. All right.
There it is.
Perfect.
Okay, so I mentioned this when there's only a few people on, but I think I'm a little over my head here in this presentation. I think I was too ambitious for trying to connect some ideas that I thought were going to be easier to connect. And then this paper that we're going to go over is, I think, a little outside of my comfort level as well. So, so just bear with me, I guess. And hopefully there's at least going to be some good conversation that can come of this. And then so after admitting that I'm kind of over my head in the topic and the paper, if there's anyone that wants to jump in and kind of drive the conversation in a different direction or help me try to make some of these points or argue against some of these points, I'd appreciate that. So last time we talked about foundation models, and I think I went over that the kind of the core thing about the foundation model approach, the way it could be successful is the self-organization of data when you have a large neural network, usually a transformer that is learning in a self-supervised fashion, that there emerges a self-organization of data where you can have a mapping between some input space and output space in your model, where the weights that the model has learned allows the model to self-organize new data that it hasn't seen before into the patterns that are going to be useful for making a prediction of a phenomenon that it wasn't necessarily trained to make a prediction of. So this, I think, is the core idea behind how foundation models work. And what we talked about last time is in earth sciences, if we're going to have a successful foundation model, we need to show that there is a self-organization of data where it allows us to make use of a model that was trained to do one thing, and have evidence that it's able, through this self-organization of data, to do something else. And so that happens when these patterns emerge in the network weights that allows this mapping. So that's the core idea. So the way I'm seeing this is that there is this emergence of patterns that happens when we're training a model. And so emergence, I put these definitions in last time, and I don't remember exactly where I got them, but emergence is a phenomenon where collective behaviors of a system cannot be simply inferred from the properties and behaviors of the individual components. So that is what the emergence is. And this happens, I think, in physical systems, where you have particular patterns or behavior that happens from a collective, that if you look at any individual in that collective, you can't necessarily get the idea that these patterns emerge. And then an example we'll talk about is flocking of like birds. So if you look at the behavior of one individual bird, there's no way that you can get the idea that there's a group of birds that are flocking together. But when you have birds that are all flying together, sometimes they're flying in a chaotic way, and sometimes they end up flocking together. And that flocking is the emergent behavior. So I guess what is really motivating me here is that there's this behavior that we see in natural systems, and we also see the same behavior in models. And then I'll talk about this a little later, is that we see it in not only neural network models, but also conceptual models of a physical system. But I'll also show a figure that I think is really interesting, because even though that we have this behavior in our models, the models don't actually necessarily represent the physical system the way we want them to. So that's what's motivating me to look into this topic. And so the first time I actually started thinking about this is when I saw this paper, non-reciprocal phase transitions, and this is what got me thinking in this way. And I read through the paper, and I thought it was very interesting. But then this last week, when I tried to go through it in a way that I can explain it, I realized that it's a little bit over my head. So I'm going to do my best, but this is like a really complicated topic that I think is a little beyond my skill level, but we're going to try. So the consequence of non-reciprocity on the collective behavior of many body systems is that's kind of what this paper is trying to show, is like what happens when you have collective behavior in many body systems, where each element of that many body system doesn't necessarily reciprocate with every other element. And what that leads to is emergence of different types of phases. And there's some phases that are kind of completely chaotic, and then you have the emergence of these phases which are pattern, that can be described with patterns. So those phases are synchronization, flocking, and pattern formation itself. And the idea here is that in physical systems, these phases are spontaneously broken at certain times, and then they're spontaneously restored. So through either some forcing or some internal dynamic, the phases emerge, and then they're spontaneously broken, then they spontaneously emerge again. And then this paper claims to lay a foundation for a new theory of this pattern formation to different physical systems, including biological neural networks. And then they also make the claim that this is the same phenomena that happens in artificial neural networks. And that's kind of where I'm trying to bring this conversation, is that through the training of a foundation model, you have these emergent phenomenon that is what makes the foundation model work, is this organization of the collective of a system that can't be explained by the individual components. So they use this as their example in many of the figures. This is a model where you have interacting agents. One agent is N, one agent is M. In this situation, this is a simple example where you just have waves with, so two agents, each with their own wave characteristic. And that's represented by theta N and theta M. And the non-reciprocity here comes on the individual agent level, where agent M tries to align with agent N. but it could be the case that agent N tries not to align with agent M. And so they have this dynamic where one agent is acting on the other and the other agent is not reciprocating that interaction. So this is the non-reciprocity on the individual component level, but then this emerges into non-reciprocity in the collective. So we'll show some figures in a second, but this is the main model that this paper is dealing with. So in a very simple example of these types of this type of behavior with two agents, you can have a disordered system where the agents are not they're not reciprocating behavior, and everything that they're doing looks just very disordered. Then there emerges alignment between the agents. So that's when, if you're looking at just waves, the agents match up in their wave space. So then they could be completely aligned. The opposite of that is anti-alignment, where they are completely it's still you get a pattern formation from anti-alignment, but they're completely opposite of each other. And then going back and forth between disorder and alignment and anti-alignment, you have these phenomenon here where you have a chiral system where let's go back. In a chiral system, they're kind of working to get either into or out of the disordered phase. And then you have these this swap system where they're not aligned, but the characteristics of their behavior are almost aligned, and you still get these pattern formations. So with that, their description here is that they might be jumping in the wave space. They might be jumping by a specific period. In this case, it's like pi. So they're not exactly aligned, but what's making them different is something that has the characteristic where you're getting a pattern from that. So this is like a simple representation of the disorder, alignment, and anti-alignment, and then what happens in between those phases. Okay, and then there's 3 phases of the alignment that are demonstrated here. You have the synchronization phase, where they're aligned in a way that they are all doing the same, acting in the same way. The flocking phase, they're not necessarily acting in the same way, but they're all acting, the agents are acting in a way that are all harmonious, but they're not necessarily showing the same behavior. And then the pattern formation phase, which isn't necessarily all the agents are acting in a cohesive way, but what you get out of it is some recognizable pattern. So what this paper is bringing is this idea that you have these exceptional transitions here, where you can go from an anti-alignment phase, you hit this exceptional transition, and then you get into this disordered chiral phase, and then at some point you can jump back spontaneously to alignment or to anti-alignment. So it's this exceptional transition which makes is what is changing spontaneously from one phase to another. Okay, so that's just a little bit of simple background or not simple, but the basics of the paper, but then to kind of bring a little more intuition on these ideas. So I want to talk about reciprocity. Here it says in equilibrium, lack of reciprocity is the rule rather than the exception. So this actually comes directly from a YouTube video that I saw the author give on this paper. So I kind of took some of these ideas from him. I made my own slides, but there's a video where the author is given a presentation on this paper. So I took some of these ideas from that. So you can have a phase transition in equilibrium. If you have just like a cup of ice, the ice can melt. There's going to be something that changes in the material, but since it's in equilibrium, if that phase goes back to ice, it's going to look just like it did before the phase shifted. So you have a phase transition here in equilibrium where you start from one system, the phase transitions, and it goes back to that same system. So this would be a reciprocity between the phase transition. But out of equilibrium, if you have a melting ice cube on a soil column, what's going to happen is that is going to infiltrate into the soil column. Then you're going to get some dynamic through the soil column. If that material, if that water then freezes again, you're not going to come up with an ice cube at the top of the soil column. Something else is going to happen. And so this is the idea of a non-equilibrium and non-reciprocal phase transition as a whole. So not on the agent to agent level, but the whole system as a whole. And we'll see that through some of the ideas in this paper, they get at the hysteresis effect, which is something that is very common in hydrology, specifically soil hydrology, where if you go through a wetting phase, then a drying phase, you don't go through the same phase space. The phase space is different between that wetting and that drying. So you have a non-reciprocity there. Okay, and then here is the motivation that I'm kind of getting at here is that when you have these phase transitions in physical systems, specifically hydrological physical systems, you have these spontaneous shifts in the phases, which are those exception points, which are really sensitive to initial conditions and really hard to predict. So the example that really started to get me a little bit more interested in the topic came from some work that Tad was doing in the Summer Institute with modeling flow through soil columns or soil moisture through soil columns and trying to predict runoff from a soil column. So if you have some soil column with layers with different characteristics, you're going to have some wetting curves that don't necessarily align a lot of the times. And so you start trying to predict the runoff from a soil column is really tough because you have to get an alignment of response through multiple layers of the soil column. And so if you look at a vertical profile of the soil column and the water content in that soil column, this is pretty typical in soil hydrologies where you see these jumps through the layering, where one layer you might have a larger capacity for soil moisture and another layer you might have a smaller capacity of soil moisture. So to get runoff, you have to have this alignment between the different layers of your soil column. And that alignment is something that happens when one layer in the soil column gets saturated or unsaturated, causing the layers above it or below it to behave differently. So this is a classic thing in soils. Oh, I had one more figure I wanted to show there. Okay, so this is a video that I stole from YouTube from Brennan Smith. I didn't make this, but I should make my own hydro simulation to show this. But I'm going to show this video, which I think demonstrates this quite well, where you have a soil column here on the bottom. You have precipitation coming in the top in blue. And then this is something we've all seen before, but when you get a big precipitation event, at this point, you've gotten precipitation coming into your soil column, but there's no runoff yet. And then you hit some critical point where runoff starts and runoff ends. And so this is that what I'm getting at is that this represents the synchronization of processes. And so it's not necessarily easy to guess when that synchronization of processes will happen to create the runoff. So obviously, if you get a lot of precipitation onto a soil column, it's going to cross some threshold, but knowing where that threshold is something that is really tough. And I think the reason that it's so tough is because of you have to get the synchronization between the hydrologic phenomena. So you can see it through this time series, a couple of examples where you'll get some precipitation, but no runoff. And that's because it did not hit that threshold. Or that it's because what I'm getting at is that the elements of the soil column don't align. The response of the elements of the soil column don't align until you get to some particular phase transition. So that's why I think that this idea of phase transition is an important one for hydrologic phenomena. So I'm talking about physical systems here, but I also think that this is exactly what's going on in models of physical systems as well. Okay, let me see if I can go back to the previous slide here. All right, so this is another figure from the paper that shows these phases, the disordered phase, the aligned phase, and the anti-alignment phase. And then you see that the agents in the system, in the chiral phase, they are acting in a way that they're not reciprocating, so they are interacting with each other. But what's happening is that you have this this kind of disordered interaction between them, and then they hit these points, these critical points, where they switch from that disordered phase to the alignment phase. And so that is something that in this paper, they're connecting with bifurcation theory. So there's actually been quite a few papers showing this phenomenon in hydrology as well in the literature, but there's these phase transitions where you have these really these critical points that are really sensitive to the actual conditions of the system, and this is what they're connecting the phase transitions in these non-reciprocal systems to these critical points in bifurcation theory. And so this would be the critical points where the phase shift happens, where you have components of your system that go from disorder to alignment or disorder to anti-alignment. Okay, so this is where they discuss this happening in specific systems, which leads to hysteresis. So where you have a phase going through a system in one direction, and then if you go back through that system, the phase shifts going the opposite direction through that same system. You're not going to go through the same path in the phase space. So this is something that in hydrology we're very used to. Sorry, my slides are out of order. So this is something in hydrology we're very used to seeing, and again from the soils domain. Hysteresis is something that is very common, where you're going from wet to dry. You don't go through the same path through phase space. So I'm going to go back up to here. So they do show this with that same Kuramoto model. They show some hysteresis exactly as we see it in soils. They see that in their simple model that they're using. Okay, and then this is an example of a simple two-agent system where you have it, and this is the same free energy kind of diagram that we've seen in terms of like really basic concepts of information theory, where you can be in one phase where you're in one energy state, and you can transition to that other energy state, and the transition is the flipping from one phase to another phase. So in this situation, the agents are acting in one manner with a clockwise interaction, and then they transition to a counterclockwise interaction. And I kind of forgot the details of this figure on the right, so I'm going to skip it for now. But oh yeah, sorry. This shows what this shows the how if you have more than two agents acting in the system, this shows the standard deviation of the fluctuations decreasing. So if you have many agents acting in the system, the way that this transition happens is going to be more, I guess, more uniform. So this is that hysteresis point. And okay, so we talked about the hysteresis. So this they describe the different types of phases that they have in their system, and this is that simple model that they're using. But they have flocking, synchronization, and patterns that emerge from this simple system, and they try to describe the phases based off of the type of state they're in, and then the type of patterns that the type of interactions that they're having, including flocking, synchronization, and patterns. Okay, so that is the pattern formation in physical systems that they're representing there. So that what I'm getting at is I do think that this phase transition is something that happens naturally all over the place, and that is like when we are interested in hydrologic phenomenon or phenomenon that we're representing within in geosciences in general, what we're looking at are these phase transitions. So this is a classic example of phase transition where you're just looking to see how much percolation happens in a system. So in this percolation example, each element in the system has some probability of percolation. So you can have a probability of percolation that's low, And let's say you have green here is representing like some phenomenon that percolates through a system. This is not a soil column, but this is a representation of a system where you have nodes that interact with other nodes. The probability of interaction between one node and the next node is P. And if it's under a critical point, then your percolation will stop, because at some point you get to the probability of continuing is low enough that at some point the percolation just ceases. So you don't continue with that percolation. If the interaction between elements in your system are at the critical point, you can keep percolating forever, but you're not all elements of your system are going to have that percolation that come through it. But if your probability is above that critical point, so this is the probability that each element in your system is going to receive something from its neighbor, you get this phase transition where you've gone from the percolation ends, the percolation is critical, so it continues forever, but you can see through the system it's confined to specific pathways. And then if your probability of percolation is above that critical point, then most aspects of your system are influenced by their neighbors. So if P is 1, then every element in your system is going to have percolation through it. If it's 0, then no elements of your system is going to have percolation through it. And if it's somewhere in between, you're going to be in one of these phases. Either the percolation is going to stop, the percolation continues, or the percolation is prevalent. So this is like the classic example of percolation. And so this is what I'm trying to, I guess, figure out is like when we this is a model. This is not a model of a physical system. This is just kind of a synthetic model of a hypothetical system. So we set our model up to represent this. And this is also, even though it's a hypothetical scenario, it is representative of many physical systems. And so when we train a neural network or any type of model, what we're actually, this is what I'm trying to get at, was we're getting these phase transitions that happen through our models. And those phase transitions are what we then use to represent reality. Sometimes those phase transitions are easy to predict, and sometimes they're hard to predict. So this is another idea that I'm trying to tie in here. So we're kind of coming from a few different places. I'm trying to tie in a few different ideas, but I do think they're all connected. This is the idea of computational irreducibility from Stephen Wolfram, where you have a system. This is a cellular automata system. This is called Rule 30. I think so. I guess I should have probably had a slide explaining this, but cellular automata and is a system where you have stepping through a system. Every cell in your system has a possibility of getting into a specific state, and that comes from its the cells in the previous state. So if you start with one cell in a positive state, the next step you might have 2 cells or 3 cells that get into a state based off of the state they were in before. And these are extremely simple rules. The rules are something like, if I have 2 positive states above me, then I'm going to be negative, or if I have 1 positive state above me and 1 negative state above me, I'm going to be positive. It's some really simple rule like that. This is the famous one called Rule 30, where the rules as you step down the layers of the system or the states of the system, they're extremely simple rules, but what emerges is these patterns within the system itself. And the key aspect of this is that these patterns are not predictable unless you run out the computation. So if you take any horizontal line on this system, you're going to have what appears to be randomness in all of the states. But if you look at it step by step by step, you see the patterns that emerge from this cellular automaton. But at any horizontal line here is computationally irreducible from the previous line, which means that you cannot predict the state of that step without computing the state of the previous step. You can train a model or a neural network to make that prediction of that that state, and you can train a neural network, for instance, to make an accurate prediction of that state. But what that neural network has to do is come up with some computation that it goes through. So if you give a neural network, let's say the state at step 10, and then you ask it to predict the state at step 50, it can do that. But what the neural network ends up having to do is go through the computational steps. So it has to learn something that is either the specific rule or something that is similar to the specific rule. So the model has to learn a computation that is an approximation of the actual system. And through that computation, the model necessarily would have to learn the patterns that emerge from the real system. So that's the idea. That's why I'm trying to connect this here, because there's this very simple system, another very simple system where there's patterns that emerge from the simple rules of the system. They look, from one angle, it can look just completely random. Any particular horizontal step in the system looks completely random. But if you look at it step by step, you see patterns emerge. Those patterns are not, you cannot predict those patterns without computing step by step. So this is what Stephen Wolfram calls computational irreducibility. I don't know if there's formal proofs of this, but there's pretty good evidence that this is the case. So that means in the physical system, you cannot, or with your model, you cannot jump ahead 10 states and guess what it's going to be without doing some sort of computation to get there. And so what I'm getting at is that the model is learning some sort of emergent behavior as well. So you have a physical system or a synthetic system that have some emergent behavior, and then your model necessarily has to have some emergent behavior as well. It's not, doesn't have to be the same emergent behavior, but it's going to be some emergent behavior. Okay, so this is a pretty jumbled presentation here, I think. But what am I trying to say? That foundation models, so these are the big neural networks that are going to be self-supervised learning on lots of data. They're going to learn emergent patterns in the data. The patterns that represent physical systems are phase transitions. Those phase transitions are very sensitive to initial conditions, which makes them hard to predict under certain situations. And they're computationally irreducible. Neural networks and physics models both can represent these phase transitions, but under some situations, particularly when those phase transitions are spontaneous, our models don't do very well. And the spontaneous phase transitions are also computationally irreducible. Those are the ideas. So here is some evidence for that. So Hoshin asked me to make this plot a while ago, where you show the performance of hydrologic models in the y direction as a function of the aridity index here in the x direction. So what I'm showing here are about a dozen different models. Some of them are physics-based models, some of them are conceptual models, and some of them are neural network models. And they're all either trained or calibrated to do the same thing. As you get more arid in any particular catchment, the probability of success of your model decreases. And what's really interesting to me about this plot is that it's not like a sharp decrease, it's like a continual decrease. So there is an idea that maybe it's not the models that causes this decrease, but maybe it's disinformation in the data that causes this decrease. But I think that it's the situation with the models because the slope here is fairly constant. There's not like a specific drop off. This isn't, although you can, if you place this on a map of the US, so these are all US catchments. If you looked at the catchments on the right here on a map, you'd show that they're all kind of clustered in specific geographic areas. But in this, because we're seeing like a fairly constant drop off from left to right, I don't think that there's any like geographical significance that would make it seem like the data is specifically disinformative. So I think there's something going on here with the models. But what's interesting about this is even as you go further and further on the right of this plot, what you would see if you actually looked at the physical system is more spontaneity in the phase transition. So if it rains on a soil in the more arid regions, the ability of the layers in the soil column or the other hydrological phenomenon that's going to influence that system to synchronize, cause runoff, and give you a value that you can try and predict, that's going to be more and more spontaneous because there's less events where there's a lot of runoff to predict. So there's less events where there's lots of precipitation. And so it ends up being the case that it looks more and more spontaneous if you just take the precipitation and the runoff. It's going to look like a more of a spontaneous hydrologic response. So what's interesting about this, and this is getting back to the rest of this presentation, is that the emergence of the synchronizing behavior, I'm saying, occurs in the real world. And I think it occurs in deep learning models. And I also think it occurs in physics-inspired conceptual models. So the same phenomenon is happening, real world and different types of models. But as you increase the spontaneity of the system, the ability to make those predictions decreases. So bringing back to the idea of the foundation model, there is patterns that emerge within the foundation model that allow us to use it that will allow us to use it for different purposes. But those patterns are going to be more and more spontaneous depending on the type of situation that we're using. And then this is kind of crazy here. This is what I'm actually working on now. And this is like these ideas are kind of driving this project that I'm working right now, where if you look at hydrologic systems and the models we create to represent them, I think that most hydrologic systems are generally, when we conceptualize them as a system of buckets. And that's true with most hydrologic models. Even if you take a soil column and break it up into specific soil layers, those buckets might act according to a different rule, Richard's equation, but they're still buckets flowing into buckets. So I think you can conceptualize any hydrologic system as an arbitrary system of buckets. And I also think if you create a network of buckets, it gets approximately similar to what a neural network is actually representing, like the equations that the system of buckets needs to what the equations you need to represent that system of buckets will also approach the same equations that you would need for a neural network to represent a system. So I think there's an equivalence between our conceptualization of hydrologic systems with buckets and what a neural network is actually doing. And my hypothesis is that for any arbitrary bucket network, there's a set of parameters that can make the response approximate to any other network of buckets. And so this is like a synthetic example of this situation where I created an arbitrarily fixed network of buckets. Like this picture shows, just some number of buckets flowing into some number of buckets flowing in some number of buckets, with the connections between those buckets being controlled by a parameter that represents a valve between those buckets. And you can create a secondary network which has a completely new arbitrary amount of buckets in it, and there's some set of time varying parameters that can make an equivalence between those two. And this also is the case with a neural network itself. Okay, so my final kind of point here is that a foundation model that we use in geosciences could end up just looking like this, like arbitrary system of buckets or whatever other conceptualization you want, but there's going to be patterns that emerge through the training of that bucket network, or that whatever network you're going through, and the emergence of those patterns will make it useful in other situations. So this is, I think, completely roundabout, and sorry for that, but this is my ideas of emergence in models. So that's it. So hopefully we can have a discussion of this. And yeah, sorry for the jumbled presentation. Hopefully it made some sort of sense. So I'll go back to this slide because I think this is kind of has a lot.
Thank you, Jonathan. We actually have some comments in the chat if you want to go through them quickly. I think Jasper, he already left, but he left some comments about the example of KGE versus aridity index, and also on hysteresis.
Okay, Jasper's comments. Let's see. About KG versus aridity, it could be also that the KG emphasizes aspects of the hydrograph. Yeah, that's true. That's absolutely true. I don't know if that's much different than saying it in the way that is in terms of spontaneity. So if you look at the aspects that KG is capturing in a hydrograph, if you look at a hydrograph in those arid regions, it's still, I think it can be characterized as spontaneity of response as well. And then about hysteresis as a result of non-symmetric pore geometry. Yeah, that's kind of capillary action. So do they provide a computational explanation? So the physical, so if hysteresis is a result of non-symmetrical pore geometry, is there a computational explanation for that as well? So the question is if the question is, if Jasper's question, he's not here, but what he's saying is that does the computational result of hysteresis, does that correspond, or is that, can can you describe hysteresis from a computational point of view that is different or the same from a physical point of view? And that's a really good question. I don't know the answer to that, but oh, actually I was looking this up. Yeah, I was looking this up. So the I think that the hysteresis that you see in computational models is because, so Jasper actually talks about non-symmetry of the pore geometry, but what the hysteresis in computational models is a non-symmetry in the elements of your model, and that is what this actually comes from this paper as well, is that is the non-reciprocity between the elements of your model. So the non-reciprocity, so one element tries to interact with another element, the other element doesn't interact the same way going back. I think that computational non-reciprocity is this would be, I think you can characterize the same it similarly as the non-symmetry of pore geometry. So if you have a pore that like in a soil column that starts like, wide and then goes small, if you go the other way, you're going to have a different result because it's harder to get through the small end of the pore than the big end of the pore. And I think that is the same thing as the computational non-reciprocity. I don't know. So that's my answer to Jasper, who is and Hoshin shared a link to the simplicity theory, which I will look up at a later time. And then
So here's a question.
yeah, please.
I think I understand your main point, which is that, well, I understand it as there are these threshold-like behaviors. Let me put it in a different terminology. In the sense that certain combinations of events have to align in order for a system to generate a response. Okay, all right. And so part of the challenge is having a computational mechanism which allows you to represent those kinds of events. And there may be some inherent challenge due to uncertainty and so on in precisely computing things so that the alignment happens just perfectly, so that the response is generated. So it's a complex problem in that sense. Yeah. Okay. And you're referring to that as a phase transition, okay, in the sense that you're moving from one state of action to a different state of action. Okay. Then you gave the example of hysteresis, and the truth probably is that I don't understand it well enough. However, I always have in the back of my mind this idea that it's always possible to make a simple problem appear more complex by some action or the other, right? Actually, John Cassidy said it the other way. He said, "There's no system, no matter how complex, that cannot be made to appear even more complex." And I've always wondered if the issue of phase transitions was not, at least in some part, related to the fact that you were trying to study the behavioral system in a lower dimensional space than you ought to be. In other words, the representation in 2 dimensions instead of 3 dimensions, where what would be a simple cyclical path in 3 dimensions because when you're filling, you have a state, which is a state called filling. And when you're draining, you have a state called draining. And if you ignore the fact that you're in a filling or a draining state, which is another variable that you have to track, you get this appearance of bifurcation on your two-dimensional phase space plot. Whereas if you plotted it in a third dimension, you might actually just get a continuous loop. And it's just because you're projecting from a higher dimension down to a lower dimension that you're starting to see this behavior that looks complicated and perhaps is actually not. Just that there may just be the fact that you can only traverse the loop in one direction, and there may be many reasons for that. You explained some of them, poor geometry and so on. So it's easier to go in one direction, you got a resistance to going the other direction, so you follow a complete path to come all the way back, something like that. So I like your main point, which is that if you're going to build foundation models, there needs to be some mechanism within them which enables them to learn that the system has to cross thresholds in order for responses to be generated, and so on, and that might be a complicated thing. I'm just wondering if the problem is not one of actually just finding the correct embedding, the correct representational embedding, which allows for a computation that's simple and makes sense. Whereas if you use a different embedding space, you end up with something that appears to be much more complicated than it actually is. And I'm saying this because right now I'm very much I've been very much caught up in discovering that the trick to building a machine learning model that works well is very much tied up in the design of the embedding space. So if you're going to do a transformer model, a natural language model, you have to learn how to embed your words in such a way that vector space operations in that embedding space make sense. When you add two vectors together, or you subtract two vectors, they have semantic meaning. So that these simple operations that can be carried out by neural networks correspond to semantically meaningful operations in the space of language. And so the interesting question that that I don't think we've faced as a community necessarily is we just take our data and we stick it in a neural network model and we expect to learn something. But it's not clear to me that when we build the embedding of that data, we just treat the data embedding that comes straight out of the machines that measure them, and we just stick it in that way. And for example, if you've got stream flow of 10 meter cube per second on the rising limb and 10 meter cube per second on the falling limb, and all you feed in is the precipitation value, the embedding doesn't have enough information to determine whether your next value should be larger or smaller. It has to somehow infer all of that in some complicated way. Whereas if you gave it the previous streamflow value, then the network would very easily be able to infer that, oh, I'm on the rising limb of the hydrograph, and therefore my prediction should be different than when I'm on the falling limb. Anyway, sorry, that was a bit convoluted, but I'm just wondering if sometimes a lot of these problems are just not related to how we actually formulate them.
Yeah, that's I think a lot of really good points in there, Hoshin. And the one thing I think about the first point about the dimensionality, like I totally agree with you about that. And didn't really think about that at all while I was putting this together. But I think, I'm not sure, but I think for the case of a foundation model, it does come down to having to transform your new use case into a dimensionality that corresponds with some of the patterns that the foundation model has put into a lower dimension. And so I wonder if there's another, I might be wrong about that. I'm not sure, but that might be if that's not the best way to do it, then we might be looking at the wrong tool. And I think that's the idea about just looking at the missing dimension in the phase space makes the problem a lot simpler. It's extremely important. But I don't think that's what a foundation model can do, unless, like you said, it's about coming up with the correct embedding space, which.
Well, it seems to me that one of the main things that the early layers of a deep neural network is doing is it's trying to learn a meaningful embedding. It's taking the data and it's transforming it in many different ways. And part of its job is to learn that meaningful embedding, which can then be easily decoded. Whether our deep networks have the wherewithal to learn the most efficient embedding or not, I don't know. You know, there may be some limitations in the particular mathematical structures that we use and so on. Or whether you would have to go through so many of these very basic, simple operations to be able to get this just right. I don't actually know. But we know, for example, that, or there seems to be some evidence that convolutional neural network processing of imagery learns an embedding which is not necessarily consistent with the embedding that we as human beings learn. And therefore it's subject to certain kinds of adversarial attacks that human beings might not be subject to. And probably vice versa, human beings learn an embedding which is probably subject to other kinds of adversarial attacks, and that's why we have hallucinations. But,
what do you mean adversarial attack? Can you describe that?
The classic thing in convolutional neural networks is that you can take an image, you can train a convolutional neural network to recognize images and classify them correctly at a very high level. And then you can take an image, and if you know how that network was trained, you can design a very small amount of noise which is added to that image, and then the network will completely wrongly classify that image. Whereas a human being looking at that image plus noise would say, oh, that's still a panda. It's not, you know, whereas the network all of a sudden decides that it's a cheetah or a teddy bear or something else, right? Or it takes number 9 and it misclassifies it as a number 0 or 1 or something like that. And people are very concerned about that because if you're going to deploy machine learning based algorithms as automated algorithms to manage systems in the world, if a person knows the network structure and knows the parameters and everything, they can very easily design, and there's a lot of theory now, they can very easily design a very simple adversarial attack which will cause that system to malfunction.
Mm-hmm.
You know, so what we're looking for is robust systems.
Mm-hmm.
Yeah. I don't know how that's related to your issue of emergence, but it seems like there must be some relevance, because if a system is very sensitive to initial conditions in categorizing states or shifting from states to another, then presumably it would be sensitive to noise. And or
Mhm.
changes in misspecification of something.
Right.
Hoshin, you were talking about the right embedding space, no?
Yes.
And you said it should make sense semantically to add two vectors. And
That's
I mean,
just because neural networks use vectors. Something else, yeah.
And so, but this semantics, I don't know, this sense of adding vectors might totally depend on the final question we are interested in, and such a foundational model does not have the one final question, right? So, so we basically would need some kind of very general overarching embedding space, which I doubt that there is.
So I think we can take a page out of large language models in that people don't quite know what questions people are going to ask large language models, but you have classes of questions. And when you're learning the semantics of natural language, you are there's sort of a semantics which has emerged over a long time, which people use and understand. And what you want is your large language model to discover that semantics and represent it in a consistent way, so that when it handles language, it handles it in the same way that we as human beings are used to. Otherwise, it won't make sense to us. And it just happens that we use vector space embeddings to represent words or tokens. And what they discovered after they started inventing these things was that that these vector space embeddings somehow started to naturally observe certain semantical properties. So you could map semantics into vector operations. So if you took the vector for man and you added the vector for royalty, you would get the vector for king. And if you took the vector for king and you subtracted the vector for woman, you would get the vector for queen, and so on and so forth. So these vectors they have to represent properties of the object or the thing that you're trying to represent, and they have to represent, using vector mathematics, these relationships like opposites, similarities, based on the kind of mathematics that we're doing. And apparently, these large language models are able to learn word vector embeddings that preserve these things. Otherwise, they wouldn't be able to function. So my question is, there must be some analog to that in dynamical physical systems, geoscientific systems. It's the equivalent to semantics. I don't have a better word for it, but things that reflect the dynamics or the relationships between different things that we observe and we represent in our models. As far as I can tell, there is no well-established theory for how to build these embeddings. So you're completely correct about that. But it probably suggests that if you have a class of problems, you could learn an embedding which works for that class of problems. Maybe not for every single thing. Yeah.
I found that, Professor, very interesting, but I find that with that approach, we'll have a fundamental difficulty is that with the example you gave, royalty plus man equals king, there are very well-defined rules that we invent, but with physical systems, we may not understand the rules, like rainfall, subtracting the moisture in the soil vector. We don't know what the result will be. So with that approach, we will be creating a model of our own limited understanding.
No, absolutely. And the point is that neural networks work with a set of rules. Okay. And so the embedding has to be consistent with the rules that networks learn. And it has to learn an embedding of the physical system, which is then consistent with the rules, vector addition and dot products and so on and so forth. So it's not clear. It's not clear that neural networks use. I guess what I'm trying to say is there needs to be an alignment between the choice of embedding and the way that the network processes that embedding. And that's a challenging problem. Right now, the networks process in a particular way, and that's just it. You would have to invent another kind of network, which, you know, who's to say that vectors are the best way to embed information? This is an information theory problem. How do I take an object and how do I represent it as a vector of numbers? Because if I don't do it, I can't process it through a machine learning algorithm. It's just not possible. So it's quite possible that a vector is not the only or the best way to characterize information. I don't actually know. But given the way that neural networks work right now, Yang, for example, he's not here. Yang is here. Yang, your recent work where you took catchments and catchment models and you learned an embedding. You called it a latent space projection or something. I can't remember what you called it. But essentially, you were learning an embedding where you were able to project the model and the catchment into the same latent space so that you could do a similarity dot product operation. Am I correct?
Yeah, that's pretty much correct. Yeah.
Yeah. Okay. So Yang operated on the hypothesis that there is such an embedding that you can learn, and we don't know what it is, but we're just going to define the rules of mathematics, and we're going to let the neural network figure it out. And it worked in this particular case to some extent. Yeah. But that's not to say that there couldn't have been some other kind of embedding that you might have embedded, that you might have invented that might have worked also, right? Yeah.
Question. I have a simple question. Oh, you go ahead. You go ahead. Yeah.
I don't. Yeah, I wanted to ask if the rules and then these neural networks found are explainable. Like, can we tell why those neural networks came to certain relationships, or it's still kind of black box models?
Well, I think
what is the approach in that case?
I think they're explainable to the extent that the semantics that they learn make sense. Right. Yes. So in the case of large language models, if you take two words, I saw a saw, right? That's a sentence. The first saw is a verb, and the second saw is a noun, right? Then somehow the large language model has to disambiguate those two words, which might otherwise have the same positional encoding, the same vector encoding, and it has to transform one so that it represents a noun and the other one so it represents a verb. So it has to add additional information. It has to learn something which helps it distinguish between a noun and a verb, right? So there's some semantics in there that somehow the large language model is learning. And if you're able to follow that semantics and you know that this vector operation corresponds to this semantical change, then to that extent, it should be explainable because it's preserving some kind of important, understandable property. But you're mapping from something you understand to something that's a mathematical operation. You're saying if this happens, this is what it means, right? Because fundamentally, if I give you a set of words, and you say, what do these words mean? The only way that I can assign meaning to those words is by actually mapping them to something. So you establish a dictionary, right? So your question is kind of complicated in the sense that to a person who doesn't have that dictionary, it makes no sense. You can't understand it. And this is part of Gray's complaint, is that non-machine learning people complain about machine learning being black box. And he says, well, no, but to a machine learning person, it's not a black box. they understand the mathematical operations of what are going on. The question is, can we make the translation from mathematics to language or something? It's that mapping that's the important thing. And similarly, if we're trying to build models of hydrology, we've got all these mathematical representations, but can we make a map from those representations to something that we want to talk about? Sorry, long answer.
Yeah. And then I just want to say that, like, in terms of like what the model is learning, you can look at the actual like learning process itself and see what are the circumstances that creates a gradient chain that the model uses to learn on a specific part of the network. So that's I think like one of the coolest things is like some node in the network might have a specific weight. How it got that weight, you can map to all of the things that it has seen and track the gradient that it used to get to that weight. So it had to take several steps to get there. If it you know, it was that weight was updated 10 times, you can look at, see throughout the whole learning process, I took a step in this direction and that was influenced by these inputs to the model, or this output of the model, or this this component of the model. And you can infer then that what it learned was from the magnitude of the weight that it got and to take that step. That's like the how it learned versus the why it learned or what it learned.
There's another way in which I'm starting to understand embeddings, and that is classically, and I mean, this is not new. I mean, I'm just reinterpreting what other people have said. Classically, if you were processing remote sensing data, people would do feature engineering. So they take the remote sensing data and they would extract features from that field. And then they would pass those features into the machine learning algorithm or the computational algorithm. And then what people started doing was passing the entire image in. And then the first layers, if you do convolutional neural networks or whatever, they're learning features. So once you've learned a set of features, that's an embedding. But for neural networks to work, that embedding has to have certain properties, as I said. It has to enable these kind of vector space operations to make sense. And the last layer embedding has to be such that you can do a linear combination of those features in order to make a prediction. So what you're progressively projecting is into some kind of linear space, high-dimensional linear space. Yeah.
So I have a quick comment about model explainability. So I think in the machine learning field, there's a research group called AI alignment. Basically, they're trying to make the model interpretable by human, like aligning with human knowledge. Like AI alignment is a problem, but they also have like some very famous thought experiment. So where you trust an AI pilot that can explain every move it does for like driving a plane, example, or you can trust a human very experienced pilot, which makes explanation you cannot understand. So which one will you trust? So their conclusion is that you do not need to understand what AI is learning. You just need to test them like rigorously using different method. I think it's another perspective about like human alignment.
I think what's really interesting about that is like human intuition is oftentimes, not interpretable or explainable or even known to the human themselves. But what it is your brain has been trained to, based off of all these situations, to know, like, under these circumstances, I need to turn my plane in this direction. But
Yeah.
yeah, that's crazy. I'll bet if you, I'm not a pilot, but I know a couple, but if you ask a lot of people why you did that, they might be like, oh, I don't know.
Yeah.
Then
I think Laura was first.
Okay. Laura?
Yeah, I wanna follow up the the comment of Young, because I mean, if we are trying to and you were Hoshin were explaining about how human beings learn versus neural networks. I think fundamentally, I mean, and I'm not sure about the history of machine learning and deep learning. I kind of crossed the party a little bit late, but if you see or understand from the neurological perspective how neural networks are developed in the brain, in a human brain, it's not a matter of vector and semantics. Is more in terms of when we were, and I'm gonna call it a raw human, we actually learn by trauma and surviving, and because we didn't have a long-term memory, right? So now we have both. We have a long-term memory, and also we can learn by trauma. And so I think that's what is missing right there in how human beings actually learn versus neural networks. Is a lot of back propagation and embedding, where we don't learn like that. Now, the other thing is we are actually missing the validation. And I think, Hoshin, you made a point a long time ago in your information theory course, where if we have a baby human and a baby robot, how they will actually learn and evolve. And in theory, they should learn more or less, not maybe at the same pace, but the same. However, I just haven't seen any manuscript regarding, human intelligence versus AI. But this is just a comment of someone that is an outsider in the field.
Okay, Dan?
I have a question going back to this idea of computational irreducibility, and like I'm interested in cellular automata, and I get like, it's kind of like I come around to the beginning of not understanding anything. I feel like when I get into it, because it seems like okay, in order to predict this, predict the state at some number of time steps away from zero, you have to compute every step. That's what we're saying, right? Like there's no shortcut. So like, to me, that's the same as determinism. We don't have any stochastic component in the changes of state. We know a very simple rule, or like a very small set of very simple rules, and we have to carry them out with enough agents or enough cells, and we have to carry them out enough time steps to be able to see something like the Sierpinski triangle, right?
Yeah, but there's one aspect of, there's many deterministic systems that are computationally irreducible, like shooting a cannonball at a target. You can use calculus to estimate very accurately where that cannonball will hit. So that's irreducibility on a deterministic system.
Okay.
But I think you had more to.
No, that's a good counterexample. That's
Oh, so yeah, so they're not, determinism and irreducibility are not the same.
It's also just adding one and one and one. If you know how many time steps you want to predict this ahead, you just multiply. So that's also a deterministic system, which is computationally reducible.
Right, and there's 3 classes of rules in cellular automata, and they're not all irreducible. I think I can't remember the classes exactly, but at least one of the classes is reducible. So rule 30 happens to be a class 3 system, which is all class 3 cellular automata are computationally irreducible.
So can you define that again, just so we're very precise about the definition of irreducibility?
To make a good approximation of what happens at step n, you have to compute an approximation at step n minus x.
So you have to go through every single step in order to get there. You can't bypass steps, is basically what you're saying.
I don't know if it's that you can't bypass any steps, but you have to compute some of the steps.
Certain critical steps. Okay.
I want to make the comment that Praveen left resource about how there is a very deep relation between computational irreducibility and physical laws by Wolfram, and he left a couple of links where it is discussed. Hernan?
Yeah, I also have to give my apologies for crashing the party late. I was in another meeting, but I just wanted to mention something. Maybe it's related to this discussion. It's about a new algorithm that Meta AI came up with. It's called segment anything method, which is supposed to be a foundational method, maybe related to what Jonathan and Gray wanna do. If I might share my screen for a little, just 1 minute, and show you the paper and some of what this can do. Thank you. So it's I came up with this paper and this theory. I was teaching my advanced GIS class, but so this basically is a pre-trained model that is in the GIS platforms, and the students are using it to classify images, a variety of images. So basically, it's a big library, and they basically you provide any image that you want, and then it'll classify it using the pre-trained algorithm. So there is a library of 11 million images, 1 billion masks. So whatever you provide, it'll come up with different segmentation of those images, and it's basically using what you were talking about is the embedding. It's the important part, and then the encoder and the decoder, and then the final answer. So if the paper is here in ArcZip, I think it was submitted this year, and it explains a little bit more about the foundations. They call it a foundational model for segmentation, which I think it probably is something easier to do than in hydrology what we want to do, because they already know the rules and they have the libraries of the images and stuff. That's one of the things that you will believe is easier to do. But they have this collection of images, and you can actually play with the demo that they have. And this is kind of a framework that they work on. The encoder and the embedding is the important part. And then the convolution. And then there is a mask decoder and a prompt encoder to come up with some valid masks. Yeah. And so this if you go here to the demo, you can choose a dog, for example, here, and then the algorithm should be able to only select the dog from this image. If you go to let me go to the demo. Go to provide this salad. If you click on this salad and you click only on the beads, they should be able to only pick up this bead over here. I don't know what it would do with the wrench. Well, it'll probably only, it has some pitfalls still, but I guess it'll kind of classify based on what you want to do. Anyhow, and they have this website. I'm gonna put it here in the chat so and everybody can play with it. That's what I wanted to share.
Thanks, Renan. That's very interesting.
It's called segment anything. It's known as SAM, segment anything model. Pretty interesting.
Jonathan, is it possible to put back up that example 30 from your Wolfram paper?
Yeah, for sure. And I did look up the classes. So there are 4 classes of rules that converge rapidly to a constant state. There's rules that converge to a fluctuating state, and then there's rules that become just completely random. So if we look up rule 30, so based off the rules are based off of these patterns at state n.
Yep.
The following state becomes one of these based off of the 3 above it.
So if we could just go back to that image. So just a reflection or a question. When I look at this image, it does not appear random to me.
Right.
Yeah. There's clearly some patterns in there. Yeah.
Mm-hmm.
And one of the ways I make sense of it is by accessing, presumably is by accessing a dictionary of patterns that I have in my brain, and by mapping that dictionary of patterns onto this, and then I recognize downward pointing triangles. You know, if I take a bunch of these together, I recognize sort of parallel lines of things going on, and so on. So that there's even if one can't predict the exact sequence, right? When I look at the overall thing, there does appear to be some pattern underlying it, and of course that makes sense because there was some rule which was used to generate this thing. Okay. If we go back to embeddings and machine learning models, in the beginning, the very naive thing was you just put a whole bunch of nodes and connections, and then you allow every connection to have a weight, and then you just train the whole thing with backpropagation. And you end up with huge numbers of weights that you have to train for. And very often that's computationally just not possible, or you get stuff that may or may not make sense. And so one of the things that we do typically in machine learning is we create dictionaries, or we learn dictionaries of patterns, which are then applied. So in convolutional neural networks, when you do weight sharing, essentially what you're doing is you're learning a subset. You're not allowing all possible values for the weights. You're only learning dictionaries which you can use as basis elements. And then you can construct you can learn your weights as some combination, or your operations as some combination of this dictionary. And of course, we do that in English. We create words, and we combine words to make sentences, and so on and so forth. And it's one of the strategies that I see as emerging here in machine learning is the same thing. And it's related to information theory in the sense that what you're doing is you're taking a set of symbols, you're combining them together, you're creating patterns of symbols, and you see those patterns everywhere. So now you use those patterns to construct models of the world by combining those patterns together, and that way you don't have to invent a new pattern every time you want to express an idea or something. Yeah. So I was just curious in your in this rule thing of Wolfram, if there's some relationship there, that at some level our ability to make sense of this relies on a dictionary of patterns, but to what extent is that not ultimately enabling us to solve the problem, and therefore you have to go through this sequence of computations at every step.
So I think that's one thing that like is like it's very. I've seen a couple of videos with Stephen Wolfram, and I've been reading that book. But he mentions that you can, like, if you learn that embedding space that has that dictionary of patterns, let's say, what you're doing is you are approximating the computation.
Okay.
And I think then you can get to the point where, you know, you want to have the minimum description length of that model, but the minimum description length would be, well,
This one. Yes.
this one. But
Plus
the
the rules.
model doesn't, how can the model get there? And you know, it probably can. I don't know this, I haven't seen it, but I would bet that you can train a neural network where it just, based off of this, it gets 3 nodes and has weights with activation functions that bring you down to the new state, and that would be it.
Well, the neural network would have to learn the interpreter, right? Because this encoding that you're showing me doesn't make sense without the interpreter.
Okay, yeah, and the well, actually, maybe I was thinking something like, never mind. When you say interpreter, can you describe that a little bit more?
So there's you have to pass this through an automaton that generates the pattern. And that automaton knows, if I see this, do this. If I see this,
Oh,
do
right,
this,
yeah.
do this, right? If you didn't have that fundamental set of that operating system, so to speak,
Yeah.
if it wasn't already there and pre-programmed, then you wouldn't be able to make sense of this. It would make, it's only in the context of that interpreter that it makes sense, right?
Yeah, let's say, for instance, you wanted to train a network to predict every 5th step. I guess the interpreter, the network could learn the interpreter perhaps if it had, let's say, 5 layers of 3 nodes.
Maybe, yeah.
And then what it's doing, it's learning that interpretation. So then it's actually learning the computation, the same computation that is given by the rule, I guess.
Yeah, so if your first layer basically interpreted this rule, then you're home free, right? And then you just have to pass it through a recursion, because that's what automata is. Yeah.
Yep.
Okay.
I don't know. I think there's a lot here that's connected, and it's hard to know formally what's connected. You know, I think there's, I guess, I think personally, I want to get a lot more savvy with higher math so I can actually see if these things make sense. That's my takeaway.
Yeah.
Jonathan, there is actually an additional point that I wanna raise, and it's how can we apply this to hydrology? Because from your talk about the exceptional points and transitions, for hydrological systems, how these non-reciprocal interactions are gonna scale with the system size, because we might need to have discernible scaling laws, right, of the different behaviors that are gonna govern the different phenomena at different scales. So for instance, if you have a small system in terms of scale, then the local factors are gonna dominate, and some exceptional transitions are gonna apply to them, right? But if you go to a larger size, and to regional or global, then those factors, new factors might come into play, right? So those non-reciprocal transitions and interactions are gonna new ones are gonna become more relevant, right? And so, yeah, I'm curious about your thoughts about exceptional transitions and how it scales.
Yeah, I think that's kind of if I could try and answer that as quickly as possible, I think it's about having a model that has learned what is computationally reducible versus irreducible in both time and space to go from one subsystem to a greater subsystem to the full system. And the reciprocity or non-reciprocity between those elements and subsystems that's what I think is the key.
Thinking about this, Jonathan, it seems that there's two aspects to reducibility, maybe I'm missing something. One is there's a minimal amount of information you have to put in to seed the computation. And then the second is there's a minimal number of operational steps that you have to be able to perform, or operations that you have to be able to perform in order to evolve that system as a sequence forward in time. So what you're passing as the rule, what you're passing as the seed is your initial pattern right at the top. And then so that represents a minimum amount of information that has to be provided to the system. And then we also have to have in the system the information about how to process that stuff. And once we've done that, everything else takes care of itself. It's like if we had to reduce it to the minimum description length, it would be that initial characterization and the rule, right, about how to do it.
Would you need could the initial characterization be like an input?
Yeah, but if you're going to measure, if you're going to take the final output and characterize it by a number of bits, and you say this is the complexity, right? But that's not the minimum description length of that thing.
Right. Okay. The specific.
It's going to be the input plus the rule. Yeah, it's the same stuff that Stephen was talking about. Yeah, you're going to have to. So you're going to add those together, and if the description of the input plus the rule is shorter than the description of the final outcome, then that defines its Kolmogorov complexity, right? And it could be that you can start from a very, very simple input and a very, very simple rule and get a very complex outcome, or you could start with a very complex outcome and a simple rule and get a very simple outcome. I mean, this is kind of part of what all Wolfram cellular automata things are studying, right? Which rules lead to what kinds of outcomes?
Right. Yeah.
And of course, his rules are very simple ones in that they're typically just based on neighborhood.
Exactly.
Information.
And yeah, and I actually, Chris and I were talking a couple of maybe months ago now, but about this issue of computational irreducibility in natural systems and the real world. And I wonder, and I don't know, I think we kind of just came up with this idea maybe that if there is autocorrelation spatially or temporally, then it should be computationally reducible. But once you get out of the realm of autoregression or autocorrelation, I wonder if that's where you get to the point where there's no computational reducibility available. So I know that it's raining today, so I can guess that it's going to rain tomorrow, but 20 days from now, there's no temporal autocorrelation. So you might have to actually compute the steps. I guess that's kind of.
Yeah, but going back to the example, if I'm not mistaken now, there's nothing fundamentally different between a convolutional neural network and the cellular automaton.
Yeah, I'd agree with that.
Right? You just got a pattern and then you process it and you generate the next one. Then you move along and you generate the next one, you move along and generate the next one.
Yeah.
Right? And so it's just using local information. If you were to use some kind of attention mechanism, which looked at the string, a much wider receptive field, and varied its weights and its convolutional operation based on the pattern, you would get a more complex, but it would essentially be the same kind of thing, but with a wider context-dependent receptive field or something like that, right?
Mhm.
So that's kind of interesting because I had never made the direct analogical map between Wolfram's things and what we do in artificial neural networks, but now it starts to be obvious. Each step is like a layer in a neuron, or it's like a recursive operation. It's like what an LSTM should be able to generate, right?
Right. Or I think a more direct analogy is the kernel that you're learning in the convolutional neural network when you're training would be the rules in the cellular autonomy.
That's right. Interesting.
And I mean, I don't know this, I'm guessing, but you could use a convolutional network just on the cellular autonoma states to predict the next set of image to image. Here's states 1 through 100, predict states 100 through 200.
Actually, I was going the other way. I was thinking that you could take all the operations that we do in neural networks and you could apply them to cellular automata, right? So convolution is one. Recursion, you're already applying, but you could use gating. So you could do context-dependent convolution or attention-dependent convolution, and you could make the whole cellular automata thing much more interesting and complex, and in a sense, a lot closer to what we're doing in artificial neural networks. So.
Yeah.
Interesting. So if I could come back to this, we should probably end here at almost 12. Yeah. But I have a question that I wanted to ask people to think about a little bit. And if you have any ideas, get back to me. And particularly Dan, we're talking about description length issues, right? Information theory, we're interested in minimum description length representations as somehow characterizing the amount of information. And with words, they've learned a way to embed words as vectors and to manipulate them and to do positional encoding by adding small vectors to the vector of the word and modifying, right? When we describe objects, anything I think that we describe in the world, we describe in terms of objects, which you can think of as nodes, and relationships, which you can think of as links. Yeah. And so if I want to describe an object, I have to come up with a description of that object, which enables me to understand all of the important characteristics of that object. So if I want to describe a tetrahedron, I might say, well, I've got 4 points which represent nodes, and then their relationships are defined by these edges or these lines or whatever. And I have to give it I have to tell you the nodes, and I have to give you their positional relationship, and I have to give you how they're connected. And I have to give you all that information. And now if I want to be able to manipulate that using a neural network, I'm going to have to encode that information in some form. And that's basically the same as information saying I've got an object and I want to represent it. What's the minimum number of bits that I have to do, and how do I organize them in some structure so that I can pass it through an interpreter, and that interpreter says, that's a ball, that's a cube, that's a car, that's a person. Okay. But finally, what it boils down to is that even though I can probably reduce every object to nodes and links, I then have to construct an embedding of all the information represented by those nodes and links in some fashion that it preserves the semantics of objects and how they relate to each other in the universe. So if I've got a cup on a table, I need to be able to represent the cup, and I need to represent the table, and I need to represent on top of. And that is one semantic relationship, which is different from I've got a table and a cup, and I've got a cup next to the table, right? In transformers, we just have to worry about positional encoding in sequence, right? Which comes before and which comes afterwards. But in the real world, we have to worry about positional encoding and relationships, which are much more complex than that. We got to represent objects in three-dimensional space. We got to represent objects in time, which one came before, which one came afterwards. We got to represent magnitudes, things that are bigger and things that are smaller. We got to represent shades of color. This entire realm of complexity of different kinds of information that we have to somehow encode into some object, whether it's a vector or not, which then allows us to manipulate it in the computer. And I haven't seen anything anywhere where anybody has seemingly come up with a good explanation or a theory for how you would do that. The closest I've seen is in graph neural networks. They have tried to take this concept of embedding and say, how do you embed a graph? Which means you need to embed the nodes, the relationships between nodes, and then the properties of those relationships, properties of those nodes and properties of those relationships. And they have the same problem. They have to embed it in such a way that then they can do semantic operations on them. And it seems to me this is a deep information theory problem. And I just come back to it because in your attempt to build a foundation model, I'm wondering if we won't inevitably run across this as one of the issues that we're going to have to deal with.
So like with the segment anything model, there's one task, just segment, and then you could build a similar type of regression model, but I guess what makes it tough, I think, is all the different types of questions you might have to answer, and that I don't know even where to start, I think. And
anyway, it was a good conversation. We ended up with more questions than we started, which is always a good conversation. Thanks, Jonathan. That was great. Leela, we had somebody already who was going to follow on, I believe.
Yes, and so our next session is on December 6th. Antoine is gonna talk about large language models and causality. Okay, perfect.
In the meantime, if any of you find anything interesting on the theory of embedding, please send it to me, because it's one of the things that's fascinating me at the moment. Yeah. It was great to see you all. Thanks for joining. And once again, thanks to Leela for herding cats.
Happy to. See you in 3 weeks. Thank you, everyone. Bye-bye.
Bye.